The LaunchPad design, first implemented with the MSP430, has been a success because of two major factors. One, it's inexpensive, and two, it's expandable. Expansion is accomplished through the Boosterpack connector. The Stellaris LaunchPad implements an upgraded version called Boosterpack XL. Texas Instruments offers some Boosterpack kits, but many more are offered by third parties. One of those third parties is Kentek, and you'll be using their LCD touchscreen Boosterpack in the lab. In order to get the most from the display, you'll learn about Stellarisware's graphics library. That library includes functions for drawing images, text, and shapes on the screen, as well as implementing touchscreen buttons. TI currently makes 3 LaunchPad-style evaluation boards. The MSP430 for $4.30 US, the Stellaris LaunchPad board for $4.99, and the C2000 Piccolo LaunchPad board for $17 US. Expandability is an important feature of the LaunchPad evaluation boards. This is done through the Boosterpack connectors. The original format of that connector was on the MSP430 board. That offered VCC and ground, as many as 14 GPIO pins. Emulator reset and test could come out to those pins, and you either connected to the crystal inputs or there were 2 more GPIO. The Stellaris and the C2000 Piccolo boards have the XL format. This is a superset of the original, which adds 2 more rows of pins. You can see the outside rows of pins that are noted by J1 on the outside left and J2 on the outside right. They're joined by J3 and J4 just to the insides of both of them. This adds the USB voltage and ground and 18 additional GPIO. To give you a flavor of some of the available booster packs, most of these are from third parties. Some of these are made by TI. Solar energy harvesting, universal energy harvesting, those are by Symbit. We have RF modules with LCDs, inductive charging. The Olamex 8x8 LED matrix is stackable. The sub 1 gigahertz RF wireless module uses the Simplicity protocol. That's from Anarin. We also have a proto board down at the bottom from Joe's Bytes. TI makes the capacitive touch board. We make a couple of digital potentiometer boards. We have the C5000 audio capacitive touch board and the TMP006 infrared temperature sensor board. To round out the list, there's another proto board with some additional capabilities out there. Anarin also makes a Zigbee networking booster pack. Kentek makes a nice OLED display if you're interested in working with OLEDs. There is a LCD controller development package available, and there's a couple of adapters, one for mod boards and one for the clickboard type of modules that will plug right onto the top of the booster pack. The booster pack we'll be using here in the class is the Kentek touchscreen TFT LCD display. There's the part number. This is the 3.5-inch QVGA TFT. It's 320 by 240 and it's 16 colors with an LED backlight, and it's designed for the XL booster pack pinout. The driver circuit and the connector are compatible with the 4.3-inch, 5-inch, 7-inch, and 9-inch displays. So you can use the same connector. If you turn your board over, you can see that the flat pin or the flat cable can be wiggled out of there, and you can use that to connect to any of these other displays. The board is covered with a resistive touch overlay, and we're going to get a chance to use the display and the touch overlay in the lab. The Stellaris graphics library provides you with graphics primitives and widgets for creating an entire graphic user interface on Stellaris controlled displays. A lot of folks will go all the way to using Linux on a machine just to get a better graphic user interface. Here you can use a smaller, less expensive microcontroller and design your own. Note that the Stellaris devices, none of the ones that we've covered, have an LCD interface. That's on the roadmap, but it's not there today. The interface to smart displays, it's either done through the serial port or through the EPI port on those parts that have them. The graphics library consists of 3 layers to interface your application to the display. At the very bottom is the display driver layer. You either have to write this or you have to modify it for the target display that you're using. We've had people do this, and it usually takes them in the 2 to 3 day range to modify their display driver to fit with the board that they're working with. This means you're either going to change the resolution, you're going to change the color, you're going to change the way that it's connected. We'll see some more about that in a second. The next layer is the graphics primitives layer for drawing additional pieces to the screen. At the very top of that is the widget layer. The widgets are for tying touchscreen elements to code-based interaction. Your application code can interface with any one of these. You can interface with the display driver, because the display driver is going to control things like the contrast and so on. You may want to just send pictures and images to the screen. That'll be through the graphics primitives layer. Or if you want to use the touchscreen, that'll be through the widget layer. So your application code can access any of the layers of graphics library. The design of the graphics library has been governed by the following goals: that the components have been written entirely in C, except where absolutely not possible. Your application, like I mentioned on the previous slide, can call any of the layers. The graphics library is easy to understand, and the components are reasonably efficient in terms of memory and processor usage. Now, those two things can be slightly at odds with each other. It can be so efficient that you can't understand it. And if you can't understand it, you're not going to be able to use it. The components are as self-contained as they can be, and where possible, any of the computations that need to be performed will be performed at compile time instead of using up cycles on your CPU at runtime. So within the graphics library, the bottom layer is the display driver. That's the low-level interface to the display hardware. So routines for display-dependent operations like initializing the display, backlight control, contrast, translation of 24-bit RGB values to the screen-dependent color map. This means all the layers above will represent colors as 24-bit values. Your screen may only have 16 colors, it may be black and white, whatever it is, we need to translate those values to whatever your screen can display. The display driver also contains low-level drawing routines like flush, lines, pixels, rectangle drawing, very simple type stuff. Your hardware-dependent code, the things that you have to modify are, for example, the connectivity of your smart display to the LM4F. Is this going to be through the serial port? You're going to talk to it through the extended peripheral interface. Currently, there's no EPIs on any of the LM4Fs, but who's to say they may be there in the future. Changes to the existing code to match your display, like the color depth, the size of it, and so on. The middle layer in the graphics library is graphics primitives. That gives you drawing support for lines, circles, text, and bitmap images. Support for off-screen buffering. Many times you don't want to write directly to the display and have people see you writing to the display. Instead, you'll write to an off-screen buffer and then swap and show that buffer. Being able to have foreground and background drawing context, so you can put something behind something else. Like I mentioned previously, the colors here and above are represented as 24-bit RGB values. That's 8 bits per color. There are 150 predefined colors already provided in the map. And if you look in the graphics library user's guide, you'll find those predefined colors in the back. Also in the back of that are the 153 predefined fonts based on the computer modern typeface. In the lab, you can go in there and you can change the colors and you can change the typeface if you like to something else. All of those are listed in the back of the graphics library user's guide. And as shown in the diagrams at the bottom of the screen, we have support for Asian and Cyrillic languages. Widgets are the top of the graphics library system. Widgets are graphic elements that provide user control elements. They combine the graphical and the touchscreen elements on screen in a parent-child hierarchy so that objects appear in front or behind each other as they're supposed to. So you may have a canvas on the screen that's the grandparent, and then that will be followed by the parent that may be something like a rectangular element or some kind of color, and then in the front of that may be the child, which could be the widgets. Now that hierarchy can extend multiple layers. So things like canvases, that's a simple drawing surface with no interaction that you're going to put things on top of. You can have checkboxes to select or unselect things. You can have containers that will group on-screen widgets together. You can have push buttons, an on-screen button that can be pressed to perform an action. Radio buttons that are selections to form a group, like low, medium, and high. Sliders, we have sliders, vertical or horizontal to select the value from a predefined range. And we can also do a list box, like a pull down, which gives you a selection from a list of options. And if you take a look there on the right hand side, that's a pretty good representation of what you can see and what you can do with the graphics library and the widgets. We have some special utilities to produce graphics library compatible data structures. For instance, this FT rasterize, it uses a free type font rendering package to convert whatever font that you want into a graphic library format, and you can see the supported font types there. So for instance, if your company uses a certain type of font in its documentation or in its logo, you could use that same font on the screen even though the graphics library doesn't have it specifically in those 153. We can also do this LMI button and create a custom shaped button using a plugin for GIMP. It'll produce an image for use by the push button widget, so your push button could say look exactly like your company headquarters, or it could look exactly like your company logo. The one we're going to use in the lab is PNM to C. This converts a netpbm image file. The netpbm image file is basically, it looks like an array, into a graphics library compatible file, which is an array. It's just a C file. The netpbm image formats, you can produce those with GIMP, with netpbm, with ImageMagick. There are others. In the lab, we're going to use GIMP. There's also make string table. This converts a comma separated file, a CSV, into a table of strings that's usable by the graphics library for those pull down menus. In Lab 10, you'll use the Kentech LCD touchscreen display on the LaunchPad board to experiment with graphics library. You'll write code that places an image, text, and shapes on the LCD. Then you'll experiment with the touchscreen by adding a rectangular button widget that controls the LED on the LaunchPad board. Carefully connect the Kentech display to your LaunchPad board. Note that the part numbers on the front of the LCD display, those part numbers should be at the end of the LaunchPad board that has the two push buttons when correctly oriented. Make sure all the booster pack pins are correctly engaged onto the connectors on the bottom of the display. In Lab Step 2, we're going to use the Kentech example project provided by the manufacturer. Maximize Code Composer and click Project, Import Existing CCS Eclipse Project. Make the settings shown below and click Finish. We're going to import the Stellarisware boards, EK LM4F 120XL, Boost XL Kentech L35. This is the 3.5-inch LCD touchscreen display from Kentech. The grLib demo should be checked, and the copy project and the workspace options should be checked and grayed out. When you're done with that, go ahead and click Finish. In Step 3, expand the project in the expand the project in the Project Explorer pane, then expand the drivers folder. The two files in this folder, Kentech 320 by 240 by 16 SSD 2119 8-bit.c and touch.c, are the driver files for the display
and the touch overlay. You'll also notice there's .h files in there as well. Open the C files and take a look around. Some of these files were derived from earlier Stellaris examples, so you may see references to the DK LM3S 9B96 board, which also has a display on it. Kentech 320, X240, X16 under SSD 2119 under 8bit.c contains the low-level display driver interface to the LCD hardware, including the pin mapping, contrast controls, and simple primitives graphics. In step 4, make sure your board is connected to your computer and the LCD screen is correctly connected to the booster pack XL connectors on your LaunchPad board, and then click the debug button to build and download the program to the device memory. The project should build and link without any warnings or errors. In step 5, watch your LCD display and click the resume button to run the demo program. Using the plus and minus buttons on screen, navigate through the 8 screens. Make sure to try out the checkboxes, push buttons, radio buttons, and the sliders. That's a little difficult for us to do here, so I'll leave that to you. When you're done experimenting, click Terminate on the CCS menu bar to return to the CCS editing perspective. In lab step 6, the first task our lab software will do is to display an image. So we need to create an image in a format that the graphics library can understand. If you've not done so already, download and install GIMP from www.gimp.org. The steps below will go through the process of clipping the photo that we have here in the document and displaying it on the LCD display. If you prefer to use an existing image or photograph or one taken from your smartphone camera right now, simply adapt the steps that you're shown below. In step 7, make sure that you have the page with the sunflowers on it open in the workbook PDF for viewing, and press Print Screen on your keyboard. This will copy the screen to your clipboard. The dimensions of the photo below approximate that of the 320 by 240 Kentech LCD. In step 8, open GIMP. Make sure that it's version 2.8 or later, or some of the buttons won't be right as far as the steps here. Then click Edit, Paste. And you should see your entire display. We have 2 screens, so we have to drag over to there. You might want to zoom in if that helps you see the edges of the screen better. So you're going to have to crop the sunflowers from your display. When you have it the way you like it, in the toolbox window, click the Rectangle Select tool and select tightly around the border of the photo. When you're done that, click Image, Crop to Selection. Then click Image, Scale Image to make sure that the image size, width, height is 320 by 240, and click Scale. You might see something that looks like a link or a chain there. You need to unlink that if you need to change the perspective of the display. Otherwise, it will maintain the perspective that you started with, and click Scale. In step 9, convert the image to indexed mode by clicking Image, Mode, Indexed. Select Generate Optimum Palette and change the maximum number of colors box to 16. That's the color depth of the LCD. When you've done that, click Convert. In step 10, save the file by clicking File, Export. Name the image pic. Change the save folder to C:\Stellarisware. And then in the Tools bin directory. So it should be C:\Stellarisware tools bin. Then in the lower left-hand corner, select PNM image as the file type. This is a hard button to find. It's the plus just above the help button on the left-hand side. So select PNM image as the file type and then click Export. When you're done that, go ahead and close. Oh wait, you will get a select RAW as the data formatting type and then click Export. Then you can go ahead and close GIMP. So that whole process was to get a source image file in PNM format. So we can now take that and convert it to something that the graphics library can handle. We're going to use the PNM to C, PNM-TOC. That changes the PNM to a C array. It's a conversion utility to do the translation for us. So open a command prompt by clicking Start Run. Type CMD in the window and click Open. The PNM to C utility is in the C:\Stellarisware tools bin directory. So type, in most cases, Control-V will not work here. Type CD space C:\Stellarisware. And if you don't want to do this all in one piece, you can. Okay, and then you can type CD tools, CD bin, and then that takes you to the right point. So you can see you're in the right folder at this point. Finally, perform the conversion by typing PNM-TOC space -C space PIC.PNM space, then there's a greater symbol, space pic.c. When the process completes correctly, the cursor will simply drop to a new line. Close your DOS window. Then open up Windows Explorer. Find the Code Composer workspace in your My Documents folder. Open the folder and find the grLib demo folder that was copied here when you imported this project. Remember, this project was imported in from our lab folders into our workspace. So you can't drop the pic file into your labs folder. You have to drop it into your workspace folder. So the other thing we want to do, we want to open up a second window that has C:\Stellarisware tools bin. We want to find pic.c and copy that into the grLib demo folder. So double check yourself. Look back at the expanded grLib demo project in the Code Composer Project Explorer. So after a moment, it should refresh, and you should see pic.c there. If you don't see pic.c, right-click on the project itself, grLib, and click Refresh. that will refresh the view of the project. In step 13, open pic.c and add the following include to the very top of the file. Our utility doesn't do this for us because it doesn't really know where the graphics library is. So we'll have a pound include grlib / grlib.h. So now if you take a look in the workbook, you should see approximately what we see on the screen and what you have on there. Of course, your data is going to vary greatly. Once you've done that, save your changes and close the pic.c editor pane. If you're having any issues with this, you can find a pic.c file in the Lab 10 folder. It's of the sunflowers, I believe. In step 14, to speed things up, we're going to use the entire demo project as a template for your own main code. But we can't have grlib demo.c in the project since it already has a main. In the Project Explorer, right-click on grlib under demo.c. Select Resource Configurations, Exclude from Build. Click the Select All button to select both the debug and release configurations, then click OK. In this manner, we can keep the old file in the project, but it won't be used during the build process. This is a very valuable technique when you're building multiple versions of a system that shares much of the code between them. You can have as many different mains as you like, and then you can just switch the files in and out of your builds as you build each one of them. In step 15, on the CCS menu bar, click File, New, Source File. Make the selections shown in the box, which are a source folder of grlib under demo. The source file is main.c, and for a template, just pick none. Then click Finish. In step 16, open main.c for editing. Add or copy-paste the following lines to the top. And you should recognize most of those: memmap, types, debug, syscontrol. Here's the graphics library, and here's the driver, the low-level driver header file for the Kentech board. In step 17, the declaration of the image array needs to be made, as well as the declaration of two variables. The variables defined in these next three statements are used for initializing the context and the rect structures. That's for rectangles. Context is a definition of the screen, such as the clipping region, the default color, and the font. Rect is a simple structure for drawing rectangles. Look up these APIs in the Graphics Library User's Guide. Add a line for spacing and add these three lines to your code. We're also going to drop in the driver library error routine. So in step 18, this is what we've seen before. Just cut and paste the error routine and drop that in. In step 19, the main routine will be next. Leave a blank line for spacing and enter these lines of code after the lines above. Next up is initializing the clock. In step 20, set the clocking to run at 50 megahertz using the PLL. Leave a line for spacing and insert this line as the first one inside main. Right after that, let's initialize the display driver. Skip a line and insert this line after the last. It says Kentech 320x240x16 under SSD 2119 init. The next function initializes a drawing context, preparing it for use. The provided display driver will be used for all subsequent graphics operation, and the default clipping region will be set to the extent of the LCD screen. Meaning if we try to write something outside of the range that will be on the screen, it just gets wiped out. If I tried to put a box at 500, 500, that 320 by 240 screen can't see that. So this will clip clip ourselves or the display, so we only have that. So drop in that gr context init as the next line. So we're going to make a little routine that will, a little function that will clear the screen for us. We're going to create that function in just a moment, but for right now, add the following line after the last one. It's CLR screen open close. Great. So what that's going to do is if there was anything on the screen before, that will wipe it out. In step 22, the following function, this clear screen function, will create a rectangle that covers the entire screen. It sets the foreground color to black and then fills the rectangle by passing the structure srect, which is what we defined earlier by reference. The top left corner of the LCD display is the point 0, 0, and the bottom right corner is 319, 239, so it's 320 by 240. Add the following code after the final closing brace in the program in main.c. So you can see we've set the X, Y, minimum and maximum for the top left corner, the bottom right corner. We set the foreground color to black. We say generate a rectangle of that size, and then we hit flush, which displays it. So we just put a big black rectangle on the front of the screen. In step 23, declare the function at the top of your code right before your variable definitions so that we'll be able to use that. In step 24, display the image by passing the global image variable g under puck image into the grImageDraw API. And we'll place the image on the screen by locating the top left corner at 0, 0. If we need to adjust that because if you need to adjust that because you have a slightly different size image, you can do that later. Leave a line for spacing and then insert this line after the clear screen call in main. In step 25, the function call below, which is grFlush, flushes any cached drawing operations. For display drivers that draw into a local frame buffer before writing to the actual display, calling this function will cause the display to be updated to match the contents of the local frame buffer. So insert this line after the last. This technique is critical if you're doing off-screen buffering. In many cases, you don't want to have the customer or the person who's watching your screen see the screen update. Instead, you want to update an off-screen buffer and then swap to that off-screen buffer. This will accomplish that for you. In step 26, we're going to be stepping through a series of displays in the lab. So we want to leave each display on the screen long enough for you to see it before it gets erased. So the following sys-control delay will give you a chance to take a look at your work. Leave a line for spacing and then insert this line after the last. In previous labs, we simply passed a number to sys-control delay, but if you were to change the CPU clock speed, your delay time would change. So this sys-control clock get returns the system clock speed, and we can use that as our delay basis. Obviously, you could have the delay be twice, half, a fifth, or some other multiple of the return value from the clock. In step 27, before we go any further, we'd like to take the code we have for a test run. With that in mind, we're going to add the final piece of the code right now, and we'll insert our later code steps in front of this. So LCDs are not especially prone to burn-in. OLEDs are different than that. OLEDs are prone to burn-in. Clearing the screen will mark a clear break between one step in the code and the next. This clear screen performs the same function as in step 20, as in the earlier step, and it also flushes the cache. Leave several lines for spacing, and then add this line below the last. So in those spaces that we left there, that's where we're going to add additional code. In step 28, add a while loop to the end of the code to stop execution. Leave a line for spacing, and then insert these lines after the last. Don't forget that you can autocorrect the indentation if you need to. So if you're having issues, you can find this code in main1.txt in the lab 10 folder. You could also compare your code to what we have there in the workbook. In step 29, now would be a good time to check the build options that have been set in this demo code. Right-click on your grLib demo project, go down to Properties. The basic two that we take a look at, the ARM compiler include options. You may want to take a look in the advanced settings at the predefines. You might want to take a look in the ARM linker at the search path. So take a look at this point in the linker's file search path and note the .lib file for the graphics library has been included. You might also notice the use of two new path variables, CG tool root and SW root. You can take a look in the project properties under resource, linked resources to see where those paths are defined. You can define your own paths. You can use those paths. There's lots of capabilities here for making sure that your projects stay portable. In step 30, make sure the graphics.lib demo is the active project. Compile and download your application by clicking the debug button. Click the resume button to run the program that was downloaded to the flash memory on your device. If your coding efforts were successful, you should see the image appear on the LCD display for a few seconds, and then it disappears. So you should have seen the sunflowers on the display. When you're finished, click the Terminate button to return to the CCS Edit perspective. Bear in mind, when you're including images into your projects, they can be quite large in terms of memory space. This could possibly require a larger flash device and increase your system cost. So just keep that in mind when you're putting images into your system. Next, we're going to display some text on the screen. In step 31, refer back to the code on page 10-20 of the workbook. You'll notice we had a couple of comments there that said later lab steps go between here and here. What we're going to do is insert the function call to clear the screen, called clear screen from the last one. We were using the one that was at the bottom of the code before, so we're going to drop in a clear screen here. In step 32, next we're going to display some text. We'll display text starting at x, y with no background color. The third parameter that we're going to have here, -1, tells the API function call to send the entire string rather than having to count the number of characters and enter that into it. That makes it a lot easier. So the pieces that we're going to use are the gr context foreground set. That we're going to set the foreground for the text to be red, so the text will be red. The gr context font set, we're going to set the font to be a maximum height of 30 pixels. So we're picking a font called font CMSS 30B. Where did we find that font? We took a look in the back of the graphics library user's manual and picked one of the fonts out of there. Next is the grrect draw. We're going to put a nice white border around the screen. Next is grflush. We'll refresh the screen by matching the contents to the local frame buffer. So note the colors that we're using here. If you'd like to try some other colors, fonts, or sizes, look in the back of the graphics library user's guide. So add the following lines after the previous ones. You can see the rectangle is inside the area of the LCD display from 1,1 to 318, 328. There's the red for the foreground color. There's the font type. And then we're going to write Texas Instruments Graphics Lab 1234 right there on the screen. It took a little bit of time to get these all centered together and a little bit of experimentation. They're probably the same thing that you'll do. Right after this code, add the same syscontrol delay to give you a little bit of time to appreciate your work. If you're having issues, you can find this code in main2.txt in the Lab 10 folder. So the added code should look like what you see in the workbook. In step 34, build load, and run your code. If the changes are correct, you'll see the image of the sunflowers again for a few seconds, followed by the on-screen text in a box for a few seconds. So pay attention to the LCD screen when you click the Run button. So there's the sunflowers. There's Texas Instruments Graphics Lab. Very nice. And then the display blanks out as we programmed it to. Return to the CCS edit perspective when you're done by clicking the Terminate button. So now we'd like to experiment with drawing some shapes on the screen. In step 35, let's add a filled-in yellow circle. How did I come up with the different addresses for all of this stuff on the screen? I basically took a piece of graph paper, overlaid the screen with a couple of numbers scratched on it, and I gradually adjusted everything until I had it in the spacing that I was interested in. So what we're going to do, we're going to make the foreground yellow and center the circle at 80, 182, that's x, y, with a radius of 50. So add a line for spacing and then add these two lines. So you can see it says the foreground color is yellow, and then we're going to do a filled circle at that address on the screen. In step 36, we're going to draw an empty green rectangle, starting with the top left-hand corner at 160, 132, and finishing at the bottom right corner, 312, 232. So if I did this right, the yellow circle and the rectangle should be about the same height. Add a line for spacing and add the following lines after the last one. You can see that the color of the rectangle will be green, and then we'll put a rectangle on there. After you have those steps, add the sys-control delay to give you some time to take a look at it, and save your work. If you're having issues here, you can find this code in main3.txt in the Lab 10 folder. Your added code should look like what you see on the workbook page. For reference, the final code will look like what you see there. Now, unfortunately, the font size is pretty small to get everything on a single page. But remember, that code is also in main3.txt. So in step 38, build, load, and run your code to make sure that all your changes work. So we should see the sunflowers appear. Then we should see the text, Texas Instruments Graphics Lab. And then we should see the yellow circle and the green rectangle appear. The green rectangle may be a little bit hard to see on the monitor. Excellent. When you're done here, click the Terminate button to return to the editing perspective. Next up, let's play with some widgets. In this case, we'll create a screen that has a nice header on it and a large rectangular button that will toggle the red LED on and off. Modifying what we have here would be a little bit tedious, so we're going to create a new file. In Project Explorer window, right-click on main.c and select Resource Configurations, Exclude from Build. Select the Select All button and click OK. So we've taken that out of the path. On the CCS menu bar, click File, New, Source File. So in the grLib under Demo Source folder, we're going to create a new source file called mywidget.c, and the template will be none. If you want to play around with the templates just basically have openings for main and the rest of that in there. They may be helpful to you or not. In step 42, add the following support files to the top of mywidget.c. So you can see the memmap, the HW types, interrupts, syscontrol, GPIO, graphics library, widget.h, canvas.h, pushbutton.h, and then you'll see the other two support files for the display. In step 43, the next two lines provide names for the structures that we're going to use here to create the background canvas and the button widget. Add a line for spacing, then add these lines below the last. In step 44, when the budget widget is pressed, a handler called onButtonPress will toggle the LED for us. So we need to add a line for spacing and then add a prototype for this function. So we're going to create a little handler called onButtonPress. Remember, handler is also a term for interrupt service routine. In step 45, you need to understand the hierarchy of the widgets and the things that are displayed on screen. Widgets are arranged on the screen in order of a parent-child relationship, where the parent is in the back, and this relationship can extend multiple levels, where you have great-grandparents, grandparents, parents, followed by the children. In our example, we're going to have the background be the parent, or the root, and the heading will be the child of the background. That means the heading will appear in front of the background. The button will be a child of the heading. Then if we were to take the button and put it somewhere around where the heading is, it would actually end up in front of this. So this supports the idea of foreground, background, and being able to have things in multiple layers, one behind the other. Add a line for spacing, and then add the following two global variables, one for the background and one for the button, below the last. Rather than reprint the parameter list for these declarations, refer to section 5.2.3.1 in the Stellaris Graphic Library User's Guide. That's in your Documents in Stellarisware as SW-GRL-UG- there'll be 4 numbers after that. The short description here is that there'll be a black background. In front of that, there's a white rectangle at the top of the screen, and we'll have LED control in red inside that. In step 46, next up is the definition for the rectangular button that we're going to use. The button will be functionally in front of the heading, but physically, we're going to locate it below it on the screen. We'll see it in just a moment when we take a look at the picture. If you want to get an idea, look at a later step and you'll see what we're actually shooting for. So it will be a red rectangle with a gray background, and then toggle red LED, the text will be inside of it. When we press it, it will fill with white, and the handler named onButtonPress will be called. Add a line for spacing and add the following global right after the last. So in step 47, the last detail before we actually write the code for this is a flag variable to indicate whether the LED is on or off. So add a line for spacing and add the following code below the last. It's a Boolean red LED on, and we're going to say it's off right now. In step 48, when the button is pressed, a handler called onButtonPress will be called. This handler uses the flag to switch between turning the red LED on the LaunchPad board on or off. Add a line for spacing and then add the following code below the last. So if you take a look in there, you should be able to recognize the GPIO pin writes that we have. That's GPIO pin 1, that's the red LED, sending a 2 to that. So if it's on, if the flag says it's on, we turn it on, otherwise we turn it off. So last up in step 49 is the main routine. The steps are here to initialize the clock, initialize the GPIO, initialize the display, initialize the touchscreen, enable the touchscreen callback so that the routine indicated in the button structure, that onButtonPress, will be called when the button is pressed. Add the background and paint it to the screen. Remember, it goes parents first, followed by the children. And finally, loop while the widget polls for a button press. Add a line for spacing and then add the following code below the last. If you're having issues, you can find this code in mywidget.txt in the Lab 10 folder. So your code should look like what you see in the workbook. Managed to fit that on a single page. In step 50, moment of truth, build, load, and run your code to make sure that everything works. So go ahead and click the resume button. And if that works right, we can see that we have LED control at the top in a heading. So the LED control is red inside of a white border. We have our widget button that says toggle red LED inside of it. I'll reach around, touch the button. You can see that when I touch it, it turns gray. Actually, it turns white here. And if you are looking at the side of the board as well, when I touch this, the LED toggles. I don't know about you, but that's very cool to me. When you're done, click the Terminate button to return to the CCS Edit perspective. Close all Open Lab projects and close Code Composer Studio. If you want to reprogram the Quick Start RGB application that was originally on the LaunchPad board, the steps are in section 2 of the workshop. In step 53, how about some more homework ideas? How about changing the red background of the button so that it stays on when the LED is lit? How about adding some more buttons to control the green and blue LEDs? How about using the Lab 5 ADC code to measure and display the temperature on the LCD in real time? We could use the real-time clock in the Hibernate module to display the time of day on the screen. We could use the Lab 6 hibernation code to make the device sleep and the backlight go off on the display after no screen touch press for, say, 10 seconds. We could use the Lab 7 USB code to send data to the LCD and touchscreen presses back to the PC. Maybe we could use the Lab 9 sine wave code to create a program that displays the sine wave data directly on the LCD display. This completes the Getting Started with the Stellaris EK LM4F 120XL Launchpad workshop. If you're interested in other workshops like this one, visit the wiki site at the link below. Thank you for watching these videos, and good luck with your Texas Instruments Stellaris projects.